This computer. Okay, we're coming back with organic chemistry on our July 22nd here. Chapter 17, part 2, we're looking at the spectroscopy of carboxylic acids and their derivatives, okay? So one of the really cool things about carboxylic acid derivatives is it's really easy to follow that functional group transformation going from a carboxylic acid to an ester to an amide, whatever, in our IR spectroscopy. Our IR spectroscopy shows a lot of these changes, okay? So that's NMR, it shows up too, but it really shows up in the IR, okay? So the first thing we want to look at in that spectroscopy is looking at just that carbon-oxygen double bond, okay? And that's going to fall in that range between 2500 and 1500 right here. But as you change the electronegativity of the atom bound to that carbonyl, you start shifting where that carbonyl is. So if we look at the acid chloride, that is the most electronegative. So it's going to be the highest shifted up. So it's going to appear right around 1800. And that's really one of the higher things for it to be in a carbonyl. Most carbonyls are, centered in the 650 to 1700 range, okay, the 1650 and the 1700 range. So if we look at just aldehydes and ketones, we're going to see them way down there. Okay, so having just that electronegative atom there shifts it to its highest point. Okay, now once we move on to our, so our acid chlorides are highest, and then if we move to the acid anhydride, it is shifted up high too, but it's not as high as with the esters or the carboxylic acids themselves. And again, the ester here, it has an oxygen there, but it has that donation with the carbon group attached to it. Once we add that hydrogen to the carboxylic acid, it shifts down again. And then our aldehydes and ketones are lower. And then our carboxylic acid salts are even more, really, really farly down. So if you kind of want to think about if your carboxylic acid group is changing, look at the thing that's bound to it. The higher the basicity, the more polar that bond is, the higher the wave numbers on the system. Okay, so that's with just the carbonyl. In the OH range, the really high range between 3000 and 4000 wave numbers, we also see another change in the fact that if you have that OH on there, you get a very broad peak, just like an alcohol would give you. However, it's not quite as high. It kind of dips down over the 3000 mark here. And that has to do with the fact that it hydrogen bonds so strongly, it almost always makes a dimer. And so we see our carbonyl peak that we talked about on the last one here, but this big OH peak really covers that entire 3000 wave number range, okay? Now, if we convert this to an acid chloride, that OH peak over here goes away and we shift our peak here instead. And so we'll see this entire thing get nice and clean when we convert it to the acid chloride and when we convert it to things like esters and amides. Okay. So in the case of NMR, NMR has everything to do with the electronic drawing of the carboxylic acid carbonyl. So the hydrogens that are next to, so in acetic acid, that'd be that methyl group next to the CO double bond OH right there, those are going to be shifted higher downfield to about 2 because of that withdrawing group there. But the actual hydrogen on the carboxylic acid, it's very, very acidic. And so instead of being in the 5 range where an alcohol would be, it's actually shifted way up into over that of benzene. It's in the 10 to 12 range right there. And if you happen to have hydrogens on your nitrogen in an amide, those are very acidic as well compared to where they would be in an amine, which would be the 3 to 5 ppm range. They're actually moved up to just over that of benzene at the 7 to 8 ppm range, okay? Now, when we talk about carbon NMR, we're talking about the carbonyl carbon of the different derivatives. And so what we'll see is that all of them are shifted fairly high into the 170 to 175 range, okay, except for the nitrile. The nitrile is the only one that's not shifted way up there, and that has to do with the fact that it has a triple bond to nitrogen instead of just a double bond to oxygen and some other electronegative atom. So what we'll see here is in the carbon NMR, all of them are going to be shifted way high except for the nitrile, so you can easily tell them apart. Okay. And like in the case of ketones, you do not split through that carbonyl carbon because it's too many bonds away, okay? You can only split where you have a hydrogen within 3 bonds of another hydrogen. And so when we look at splitting, if your alkyl group is separated, oh, wait, oh, there it was. If your alkyl group is separated away from that, none of these hydrogens will split anything over here. However, these hydrogens on this side of the carbonyl will split like any other splitting pattern. So in this case here, we'll have 2 hydrogens split 3 times to give us a total of 4 peaks. This right here, let me do a different color. These right here will be split by these 2 to give us a triplet. So our triplet is there and our quartet is there. And notice this is the methyl group. I'm going to draw a line with green. This methyl, I'm going to draw it with green, really am, is unsplit because it's too far away from any other atom, any other hydrogen. Okay. So that's just a brief thing about carboxylic acids and carboxylic acid esters, where they show up in the IR, especially that carbonyl, has everything to do with what's bound to that carbonyl. Chlorides being the highest wave numbers, going all the way down to carboxylic acid salts at the lowest wave number. Okay. Questions about spectroscopy? Okay. Okay, then I'm going to move on to our slide number 3, our first set of reactions with these carboxylic acids. Okay. Now, up to now, we've actually learned about how to make carboxylic acids. We learned about it in the carbonyl when we talked about a conversion of alcohols. We know we can oxidize alcohols. And if we did it in a controlled fashion with PCC, we'll get to the aldehyde. If we did it in an uncontrolled fashion with chromic acid, potassium perchromate, or potassium permanganate, sorry, potassium chromate or potassium permanganate, those all oxidized our alcohols, our primary alcohols, down to carboxylic acids. Okay, so we already know that, but there's a couple different ways to also make them from alkenes. So for example, if you have an alkene, and it can be a cis or a transalkene, and you can oxidize that down using permanganate with a little bit of base, and that'll give you 2 different carboxylic acids. Notice that the permanganate just attacks the double bond, and where that double bond was is where your carbonyl carbon is going to be on either side. Okay, so if you'll get 1 carboxylic acid for whatever the R group was here, and a different carboxylic acid for whatever is over here. So if it's a symmetrical molecule, you'll only get 1, but most of the time it's unsymmetrical and you get 2. The other way to do that is also a reaction we learned when we talked about benzene. The only reaction we have that oxidizes benzene down to something other than what it was is the reaction with ozone. Okay, so in the reaction with ozone, we can do a benzene or this, and again, it'll oxidize that double bond, and where that double bond was is where we're going to have our new carboxylic acids. Okay, so and this it also extends to acetylene. So you can have a double bond, a triple bond, or a benzene ring. And ozone with peroxide will break those down into carboxylic acids. Okay. Okay. So we can make them from alkenes. We can make them from alkynes. We can make them from benzene derivatives. Okay. All right. Oh, and here's another way to make, there's 2 ways to make carboxylic acids with benzenes. And we learned about this again in the benzene chapter in 15. We learned that if we have an alkyl group that has at least one hydrogen on this benzylic position, that position right next to the benzene ring, if you have at least one hydrogen there, you can use potassium permanganate and it'll oxidize it, the alkyl group off to give us the carboxylic acid. Okay. However, if you have an alkyl group and you use ozone right here and the hydrogen peroxide, you're gonna oxidize the benzene, just like we did with the alkenes and alkynes. It's oxidizing the benzene to give us our alkyl group with the carboxylic acid on it. So when making carboxylic acid out of benzene derivatives, you want to make sure if you want to keep the benzene, you want to use permanganate. If you want to lose the benzene, you want to use ozone. So, and just like in the last chapter, we talked about that one reagent we can use that we can oxidize aldehydes down using a very mild reagent, the silver +1 reagent. The silver +1 reagent will oxidize all aldehydes down to carboxylic acids. And that's one way to do it. And we learned that at the end of the last chapter, right there. But the other way to do it is we can take any primary alcohol with permanganate or chromium and oxidize them down to our carboxylic acids as well. Oh, there we go. All right. So these should all be familiar. We've already talked about them, but I wanted to make sure I drew your attention to them because we're going to use them again in our homework set and our activity. And we talked about this at the end of the last chapter right here, the cyanohydrin reaction, where we're using that cyanide to add that new carbon-carbon bond and then hydrolyze that cyano group down to our carboxylic acid. And remember, we got alpha hydroxy carbonyl compounds that way, and we also got some beta ketones that way by using that and getting that and we also got unsaturated conjugated carboxylic acids that way. We could use a dehydration reaction. So don't forget that that is another way to get to these carboxylic acids. Okay, so in the case of using the cyanide reagents, you can actually use the cyanide as a nucleophile and displace an alkyl halide. In the case of doing that, we actually add a single carbon to the chain. Okay, unlike other nucleophiles where we actually don't add carbon to the chain, the cyano reaction does add a single carbon to the chain. And then so if we started out with an ethyl group here, we're going to end up with a propyl carboxylic acid over here. So that's a slight subtlety you need to remember on there. But again, once you get that cyano group on here, you can hydrolyze it down with acid or base, and we'll learn that in the next chapter, I believe. On the different mechanisms for that, and we can generate our carboxylic acid. But again, the carbon of the carbonyl here comes from the cyano group here, and just like in the cyanohydrin reaction, the carbon of the carbonyl comes from the cyano group. So it'll help you keep track of your carbons as you move through the system. Okay, all right, now this one I'm going to spend a little more time on. And this was introduced back with Grignard reagents. However, this you'll see is in the homework set. And so this is kind of going to be something I'm going to go over a little bit more. So in the case of making a Grignard reagent into a carboxylic acid, it's actually a very simple reaction. We take any halide that we can generate a Grignard from. So that means it can be primary, secondary, tertiary, benzylic, arylic, doesn't matter, okay? If you can make a Grignard reagent with it, you can turn it into a carboxylic acid, okay? And the way we do that is just react it with CO2, okay? Because if you remember, CO2 is a dicarbonyl compound, and it just reacts like any other carbonyl compound. We get attack of the nucleophile at the center carbon there, and then when we hydrolyze it when we hydrolyze it to get rid of the salt, we generate our carboxylic acid. So this is a great way to make even very hindered carboxylic acids. If you can make the Grignard, you can make the carboxylic acid. okay? And it only adds that single carbon from that CO2, okay? So the other way we can do this is if we have any other functional group already, an acid chloride, an acid anhydride, an ester, an amide, or a nitrile, we can take any of those compounds and hydrolyze them with either acid or base to get them all the way down to the carboxylic acid, making sure you acidify at the last step to make sure you have your free carboxylic acid. Okay, and we'll talk about that the hydrolysis steps and the mechanisms for that, I believe, in the next chapter. Okay, so we have a bunch of different ways to make carboxylic acids, and we've already learned most of these carboxylic acids on how to make them, okay? But we want to make sure we pull all that knowledge from last semester and this semester together to say, oh, we have a lot of different ways to make these carboxylic acids, and we can do a lot of different things with them once we have them. Okay, so now let's talk a little bit about the properties of carboxylic acids. One of the reasons they're called acids is because they have an acidic proton, okay? And in the beginning of last semester, we talked about the idea of conjugation. And one of the things we kept bringing up with resonance structures and conjugation was the acetate ion, or the carboxylic acid, where we can take that, and that proton is acidic because of the resonance stability of having that anion spread out over 3 different atoms, okay? So remember that resonance is the reason we have that acidic proton, and we can use that to our advantage, okay? So because of that delocalization here, we have pK values in the area of 5, okay? And so that means even very weak bases, like in this case here, we're using sodium bicarbonate, which is already has, it only has one basic, only one proton it can deprotonate with. Only one proton it can deprotonate. And so it's a very weak material. It'll generate carbonic acid, which then of course decomposes to CO2 and water, okay? So this is a very weak base, which means acetic acid is one of our carboxylic acids are one of our stronger organic acids. It's one of our most acidic protons we have in organic chemistry, okay? So that means that almost any base, even anything above that of the bicarbonate, will deprotonate it. So we have carbonates, all ethoxides, hydroxides, hydrides, and even ammonia are basic enough to deprotonate all of the carboxylic acid. Now, can we change the acidity of the carboxylic acid? Can we make it higher and lower? Yes, we can. And we can do that with what we call an inductive effect. If we have electron withdrawing groups that are close enough to the carbonyl carbon to actually pull electron density away from the carbonyl carbon, we can increase the acidity of that proton. And I'm going to see if I can blow this up at the bottom here. And we talked about this when we were talking about carboxylic acid, when we were talking about acidity in our acids and bases chapter. So this is kind of a reminder. But the idea here is that if you have an electron withdrawing group, an atom that is more electronegative than carbon, it can inductively pull electron density away from your carbonyl carbon. And if it does that, it'll stabilize that negative charge that is generated by the deprotonation. If it's stabilizing that negative charge, it's easier to remove that hydrogen. Therefore, it becomes more acidic. Okay. And if you add a second electron withdrawing group to it, it's going to pull even more electron density, making it even more stable, making that even more acidic. Okay. And by adding a third one to our system, the effect is increased. Okay. So we can increase that by just adding additional electron withdrawing groups. Okay. However, by moving, the further away your electron withdrawing group is, the less of an effect it has, because it has to pull through too many of the bonds. Okay. Now, I believe it's in chapter 3, the acids and bases, where this is, you can review this if you if this doesn't sound familiar. But this is a very strongly pronounced effect in the acidity of carboxylic acids. Okay, so any questions about the acidity of carboxylic acids? Okay. All right, we have about 20 minutes left, so there's a few more reactions I want to do. So we only have about 3 modules to do tomorrow before our activity. So I'm going to go on with a couple more things. Okay. So up to now, we've done different reactions on carbonyl compounds, and we've had 2 different things that we can have happen. Okay. We can get addition across that carbonyl carbon and go from our sp2 hybridized trigonal planar to our sp3 hybridized tetrahedral structure. Okay. Now, the driving force for that is the idea that we have a nucleophile coming in, and then whether or not the group leaves depends on how good a leaving group is. Is it a strong base? Is it a weak base? Is it a stable ion? Okay, so when we have attack at these carbonyl compounds, we can either have substitution reactions in which we regenerate our carbonyl, or we can have addition reactions, and it's all about our leaving group. So let's talk about leaving group ability. So in the case of reactions with aldehydes and ketones where we had addition of a nucleophile across the system, we had the choice to lose something like a hydrogen with a negative charge, a carbon with a negative charge, an oxygen with 2 negative charges. Those are all really bad leaving groups. Okay, because it's a hydride ion is really basic. Carbon anion is really basic. Oxygen -2 is really basic. So they don't want to leave. So if they're really good bases, they're not going to leave, and you're going to get addition reactions. Okay. However, in our carboxylic acid derivatives that we've just looked at, we now have more electronegative atoms. More electronegative atoms can stabilize negative charges. Therefore, it can be less and less basic, or a better and better leaving group. Once we have this OH, the chlorine, the alkoxide, and the amines, we now will undergo substitution reactions on that carbonyl carbon. Okay, so once we get to going from the aldehydes and ketones, where addition is the driving force, or oxidation, we now have something that can be substituted and will undergo more substitution reactions than we saw before. Okay? So let's talk about why this happens. Okay? So in the case of reacting an aldehyde or a ketone with a nucleophile, what we're going to see is that once we form this tetrahedral center, the only way for us to regain that carbonyl carbon is to have, excuse me, is to have our electrons that are on our oxygen come in to reform that carbonyl carbon, and it has to break one of those sigma bonds, and therefore those electrons have to leave with one of those leaving groups. Okay. In the case of an addition across something like an aldehyde, we'll have a leaving group possible is the hydride ion, okay, which is a very bad leaving group. Okay, it's very basic. It doesn't want to leave. It doesn't want to be an anhydride. In fact, it's a nucleophile. It would rather be a nucleophile than a leaving group. Okay. So in the case of if we had a nucleophile come in and all we had was an R group, like in a ketone, again, you're having an alkyl anion as a leaving group. Again, that's our strongest nucleophile because it reacts so great. So it makes it a very bad leaving group. And therefore, we rarely see substitution reactions happen on aldehydes and ketones. Okay. That's not the same for our carboxylic acid derivatives. Our carboxylic acid derivatives are more likely to undergo nucleophilic acyl substitution. That means we have a nucleophile come in and we regain our carbonyl compound at the end of the reaction. So nucleophilic acyl substitution. Okay, not addition, substitution. Okay, so But the first step in the reaction is the same. We end up having the nucleophile come in and attack the carbonyl carbon to generate our tetrahedral intermediate. The difference is when the electrons come in to reform our carbonyl, we have something that can leave with that is not too strong, that is not too basic, that can stabilize the charge. And when it can leave that way, either as a protonated neutral species or even as a halide, it will allow the reformation of the carbonyl. Okay, so this is a little bit different than what we saw with the aldehydes and ketones. We're actually looking for a lot of these reactions to have substitutions, not elimination, not be addition reactions. Okay, all right, so how do we know which things are going to leave or not? Okay, so the idea here is, can we have something leave as a stable ion? Okay, now, so we have different things like the chloride ion or the acetate ion, the alcohol, the hydroxide, or the amine. Those are all better leaving groups than hydroxide, the carbon anion or the hydride anion, because those are much, much stronger bases. Okay, so we can get these to leave as stable ions. However, their ability to leave has everything to do with their basicity. Okay, so if we look at the basicity of the chloride ion here, remember HCl is a very strong acid, so that means chloride ion is a very weak base. Okay, just like that with carboxylic acid, our carboxylic acid is not as acidic as HCl, so it's a little more basic. Okay, and then we have hydroxide and alcohols and water are both about the same acidity. Therefore, they have about the same ability to leave. Our ammonia is a little more basic, which means it's a little less. And then, of course, our carbon anion and our hydrogen anion are way up here as really, really strong bases, and they don't leave at all. Okay, so what we see in this trend is that the increasing base strength, as our base strength increases, it decreases our ability for our leaving group to leave, giving us our regenerating our carbonyl compound. So what that means is our acid chlorides here are most reactive because the leaving group is the weakened base. Our esters and carboxylic acids are less reactive than the anhydride or the chloride because of the increased basicity of the leaving group. And the least reactive of the set is this amide right here, because the nitrogen leaving would be the strongest base of the set. And of course, the ones that don't react would be the carbon and the hydrogen over here. And that's why we end up with substitution reactions as opposed to the, addition reactions instead of the substitution reactions. So the entire difference between the addition reaction with aldehydes and ketones and the substitution reaction with carboxylic acids has everything to do with the base strength of the group attached. Notice all of these atoms are more electronegative than hydrogen or carbon. All right, questions on that? You can memorize that acid chlorides are most reactive and anhydrides are, because those react spontaneously in air with water. Esters and carboxylic acids are usually stable at room temperature, and you really have to hit the amides really hard with acid or base to get them to leave. So you can remember it that way, or just think about if you're really comfortable with the pKa scale and the strong acid, weak base theory. This really defines all the different reactions, and our reactivity in our next chapter, chapter 18, is going to follow this rule of basicity and availability of leaving group. All right. People are really quiet this week. I mean, I've only had a couple comments this week, and so I'm worried. So, So if anybody wants to talk while I switch over to my last chapter, last section we're going to do today. The next thing I want to talk about is the acid chloride, because of course it's the most reactive of the set. And so I want to go over some of the different substitution reactions that we have on this. Okay. So these are the different reactive species we have available to us in the carboxylic acids for our substitution reaction. And of course, we have the acid chloride, which is most reactive, our anhydride, which is next most reactive. And notice this is a cyclic anhydride. They don't have to be cyclic, but they are particularly stable because of the decrease in entropy by having a ring form. Okay, so we'll see a lot of anhydrides actually be these cyclic anhydrides as well. Then next is the esters and amides as far as how to make them and how to hydrolyze them. Okay. But let's talk about acid chlorides. We talked about this before when we were making them in previous chapters, but there's two typical reagents we use for this. The first one is thionyl chloride, or SOCl2, and it works because it makes the OH a better leading group by converting it to something else, okay? And the other one we have is phosphorus trihalide or trichloride or pentachloride. In both cases, you're transferring the oxygen to the phosphorus, and you have a phosphorus oxygen as a very strong bond. Okay, so in the mechanism of thionyl chloride here, again, OH is not as good a leaving group as it could be because it would leave as the hydroxide ion. So what we're actually doing is we're using the electrons on the oxygen to attack the sulfonyl, the partially positive sulfur compound in the thionyl chloride to generate what we have here is a thioester group here. Okay, so we've just changed the reactivity. It's no longer a hydroxide. It's going to leave as an SO2 minus group, a conjugated negative charge. So we've turned it into a better leaving group. So once we've done that, it'll rearrange to liberate a chlorine. Our chlorine now becomes our nucleophile. Okay, the chlorine was kicked out of here to regain our sulfur oxygen double bond, and now chloride is our nucleophile. And when our chloride comes in, it goes through our tetrahedral center, and now we have to compare what's the better leaving group. Okay, in the case of this, we are comparing the chloride as our leaving group, or this complex here as our leaving group. This complex would actually leave as a neutral species. The chloride would have to leave and go backwards as a negative species. So whenever you have the option of losing a neutral species or a negative species, you typically lose the neutral species, okay? And then, so that means these electrons can kick in, regenerating our carbonyl group and having the chloride on here. And then this compound right here, even though it's neutral, will decompose to generate HCl and SO2, and both of those are liberated as gases, and therefore there is no back reaction. So notice there are no equilibriums right here, although there's technically an equilibrium in these two. Once it gets to this set here, it drives it to completion. All right, any questions on that? So really the mechanisms are not the really important thing here. The important thing is that a little bit of SOCl2 will convert any carboxylic acid to the acid chloride. Remember, it also converts alcohols, primary and secondary alcohols, to alkyl halides. So it's a really useful reagent. You can use it for two different things. Okay, so once we have acid chlorides, then we can actually, because it's the most reactive of them, we can make every other carboxylic acid derivative from it, okay? So because it's the most reactive, because that chloride likes to leave most, okay, we can use it to create all the other ones. And the next most reactive carboxylic acid derivative is the acid anhydride, okay? So we typically, to make the acid anhydride, we will use, let me blow this up, the acid chloride here, plus the salt of the carboxylic acid. Okay, if we were just to use the carboxylic acid itself, it would have a proton exchange. It wouldn't act as a nucleophile, and it wouldn't work. So we actually use an acid chloride and the acid chloride salt here. Our negative charge on our carboxylic acid salt here acts as our nucleophile and displaces our chloride. Okay. The other thing that we can do is we can actually have an alcohol come in here, and the lone pair on the oxygen will act as our nucleophile, come in and displace the chloride, and that generates an ester, and we lose HCl in that reaction. Or in the case of, sorry, I thought I muted my phone, my watch. We have the case of the nitrogen here. Now this is the strongest nucleophile of the set. So it comes in and displaces that and generates our material here, and also HCl. So we either have to use multiple equivalents of the amine or have a different base available, because what's going to happen is you're going to make a salt of whatever the strongest base is there. So the other thing you can do is also react it with water or base, and that'll take it to the carboxylic acid, which is of course about the same reactivity as the ester here, and it undergoes about the same mechanism as well. All right, questions on that? Okay, we got about 5 minutes left, so let me go ahead and, let's see, I think this is my last slide on this set here. No, maybe not. Okay, let's talk about making of amides. Yeah, let's just finish with the making of amides here. Okay, so I said before, we have to be careful when we're reacting our amines with acid chlorides, okay? And the reason we have to be careful with that is we need to know exactly how many equivalents to add, or we need to have something more basic than our nucleophile in the system. So most of the time, it's easiest to use 2 equivalents of the amine, either ammonia or a primary secondary amine, to generate our amide product plus a salt. Okay, so in the case of, if we wanted a primary amide, we want to have only 1 carbon-nitrogen bond, so we start with no carbon-nitrogen bonds in the ammonia. We add 2 equivalents. The first equivalent attacks, the second equivalent forms the salt with the HCl produced. Remember, all acid chlorides are going to produce HCl as a byproduct. Okay, so if we want a secondary amide, that means we already had to have 1 carbon bonded to the nitrogen, and so we use a primary amine that already has whatever R group we want on there, and then we will go and displace our chloride ion, generating our secondary amide plus a salt of the amine, okay? And in the case of a tertiary amide, we have to have 2 carbon bonds already on there, and then we do the 1 substitution to give us our tertiary plus some more salt, okay? So, unlike the reaction with ammonia and an alkyl halide, once you react a carbonyl with the nitrogen, it decreases the nucleophilicity of that nitrogen. So we can just add 1 equivalent of the acyl halide to an amine, and it'll stop at that primary amide. That is not true with amines. That amine is still nucleophilic. So that's a really good way to control this, and it will learn in chapter 20 that how we can actually make our amines back from this system. Okay, I'm going to stop here at amides. We're going to go with the synthesis of anhydrides. We're going to continue that later. So we're right here close to 1:40. What I'm going to do now is I'm going to stop recording and answer questions until you are ready to go. Stop.